Imagine you have two lists of numbers that contain exactly the same items, but they are shuffled in a completely different order. Your challenge is to find the exact address, or index, of every number from the first list within the second list. Can you figure out the fastest way to match them up without getting lost in the shuffle? Let's break this down from scratch. We are given two lists of numbers, which we will call List A and List B. The most important rule is that List B is just a shuffled version of List A. Every number in List A exists in List B, and every number in List B exists in List A. They are anagrams of each other. Our job is to produce a new list of numbers. This new list must be the same length as List A. For every single number you see in List A, you need to output the position, or index, where that specific number is hiding inside List B. Let's look at a concrete example. Suppose List A has the numbers 12, 28, 46, 32, and 50. Now, look at List B. It has 50, 12, 32, 46, and 28. Notice how the numbers are the same, but the order is mixed up. We need to find where the first number of List A, which is 12, is located in List B. Scanning List B, we see 12 is sitting at the second spot. Since computers start counting at 0, that second spot is index 1. So the first number in our answer is 1. Next, we take the second number from List A, which is 28. We scan List B again. We see 28 is at the very end, at index 4. So our answer adds 4. We repeat this for every single number in List A. Why is this tricky? If the lists are short, you can just look at them with your eyes. But imagine if each list had 10,000 numbers. You might find a number by scanning, but what if there are duplicate numbers? If List B has the number 5 in 3 different places, which index do you pick for the 5 in List A? You have to make sure you don't pick the same index twice for 2 different 5s in List A. The rules say the arrays are anagrams, meaning the counts match perfectly, so we just need to map them one-to-one uniquely. The challenge is doing this quickly without checking the same spots over and over again. The obvious thing to try is the method we just used in the example. We take the first number from the first list and we start a fresh search through the entire second list, checking every single position one by one until we find a match. Once we find it, we remember that index and move on. Then, we take the second number from the first list and we start a fresh search again. We go through the entire second list from the very beginning, checking every position, looking for that second number. We keep doing this for every single number in the first list. The main idea here is that we never remember where we found things before. We treat every search as if it is the first time we are looking for that number. We don't keep a list of used spots unless we manually track them, but even then, the searching itself is repetitive. Why is this slow? Because for every single number in the first list, we potentially scan the whole second list. If the first list has 10 numbers, and the second list has 10 numbers, we do 10 times 10 checks. If the lists have 100 numbers, we do 10,000 checks. If they have 1,000 numbers, we do 1,000,000 checks. This pattern of multiplying the size of the list by itself is called quadratic time complexity. It means as the data grows, the time it takes explodes. We are wasting time rescanning parts of the list we have already looked at, or parts we know contain numbers we aren't looking for right now. We fail to remember the locations of numbers for later use, forcing us to rediscover the same information over and over again. The key insight is simple. If we know exactly where every number is located in the second list before we even start looking for the first list, we never have to search again. We can just look up the answer instantly. To do this, we use a special data structure called a HashMap, or a dictionary. Think of this like a phone book or a library catalog. Instead of walking through every book to find the one you want, you look up the author's name in the index, and it tells you the exact shelf number. We will build this index for the second list first. We create an empty dictionary. Then, we walk through the second list just once. For every number we see, we record its location. If the number is new, we create a new entry in our dictionary with that number as the key and a list of positions as the value. If the number has appeared before, we just add the new position to that existing list. This handles duplicates perfectly because we are storing a queue of positions. Once this dictionary is built, we walk through the first list. For each number, we go to our dictionary, find that number, and instantly pull out the next available position from its list. We take that position, write it down as our answer, and remove it from the list so we don't use it twice. This eliminates all the repeated searching. We only walk through the second list once to build the map, and we only walk through the first list once to get the answers. We never look at the same spot twice unnecessarily. This transforms a slow, repetitive process into a fast, direct lookup. Let's trace this optimal method step by step with our first example. List 1 is 12, 28, 46, 32, 50. List 2 is 50, 12, 32, 46, 28. We start by creating an empty dictionary called index map and an empty answer list called mapping. First, we build the dictionary from list 2. We look at the first number in list 2, which is 50. The dictionary is empty, so we create an entry for 50 and add the current index, which is 0, to a queue. The dictionary now has 50 mapped to a queue containing 0. Next, we move to the second number in list 2, which is 12. We check the dictionary. No 12 yet. We create an entry for 12 and add the current index, which is 1, to its queue. The dictionary now has 50 with queue 0, and 12 with queue 1. Next is 32. We add it to the dictionary with index 2. The dictionary has 50 with 0, 12 with 1, and 32 with 2. Next is 46. We add it with index 3. The dictionary now has 50 with queue 0, 12 with queue 1, 32 with queue 2, and 46 with queue 3. Finally, we see 28 at the end of list 2. We add it with index 4. The dictionary is now complete. It has 50 with queue 0, 12 with queue 1, 32 with queue 2, 46 with queue 3, and 28 with queue 4. Now we start the second phase. We look at the first number in list 1, which is 12. We go to the dictionary, find the key 12, and look at its queue. The queue has 1. We take that 1, remove it from the queue, and put it as the first number in our answer list. Our answer list now has 1. The queue for 12 is now empty. Next, we look at the second number in list 1, which is 28. We go to the dictionary, find 28, and look at its queue. The queue has 4. We take the 4, remove it, and add it to our answer list. Our answer list now has 1, 4. The queue for 28 is empty. Next is 46. We find it in the dictionary. Its queue has 3. We take 3, remove it, and add it to the answer list. The answer list is now 1, 4, 3. The queue for 46 is empty. Next is 32. We find it in the dictionary. Its queue has 2. We take 2, remove it, and add it to the answer list. The answer list is now 1, 4, 3, 2. The queue for 32 is empty. Finally, we look at the last number in list 1, which is 50. We find it in the dictionary. Its queue has 0. We take 0, remove it, and add it to the answer list. The final answer list is 1, 4, 3, 2, 0. We are done. Every number in list 1 has been mapped to the correct unique index in list 2. You will spot this pattern when you see a problem asking you to map items from one list to another, or when you need to find the position of an item in a second list efficiently. The two signals are, first, the problem involves matching elements between two collections, and second, you need to avoid scanning the same list repeatedly for every single query. The time complexity is linear, or O of n, because we only walk through the lists once. The space complexity is also linear, or O of n, because we need to store the dictionary of indices. Try the next problem on LeetCode that uses the same mapping pattern to solidify your skills. If you found this helpful, please subscribe for more beginner-friendly algorithm breakdowns.